Sets 3 and 4. Sorry I couldn't make it today. Learning some stuff, talking about hybrid. I hope that's okay with you. I hope you didn't miss me too much. I know I miss you dearly. What's going to happen in this video? We're going to talk about 1, 2, 1, 3, and 1, 4 with this practice quiz that you should have knocked out before class started. You have this beginning intro page seen here. Hope you don't mind that. First question was asking what type of sequence is represented by this pattern here. Well, let's talk about it. What's up with this pattern? I see that there's, count them, 3 cubes here. And what changes as we go towards the right? Well, we see this new version thrown in, this L. Occasionally we take the L, hopefully we don't on this one, where we now see we have the original 3 and that new 3, getting us a total of 6. Same thing here, we have this red L, which was mentioned before, and now we have another one. DJ Khaled, another one. So we have the 3 we started with, the 3 from the previous term, the 3 now, getting us to a total of 6 squares. What do you think's changing over here? Hopefully you're saying that this is going to 12. And since there is a common difference here of just adding 3, adding 3, adding 3, that might be something important to mention on the side, is that our common difference is positive 3. And since we have just this pattern that keeps adding and adding and adding, we would say that this is arithmetic, because we just keep adding on 3. We're not multiplying or dividing, so we just keep adding 3. For the recursive, the number of squares starts at 3. And in words describing this, how do we find the number of squares in the next step? We're taking the current, and that should be equal to our previous term plus 3, because every term as we move forward is adding 3 more to the previous rendition. Pause the video, make a note of this, because I'm about to erase it. All right, hope that one wasn't too bad. Let's keep this going, evaluating functions. We have function notation here, a little intimidating, but don't let that intimidate you. We saw function notation in 1.3. So what I am going to do now is take a look back at what we saw in 1.3 with our recaps. We saw that we can use our current written as f of t and our previous as f of t minus 1. That was the pattern that we talked about. We use those terms kind of back and forth now. So f of t minus 1, whenever you see that, or in this case, f of n minus 1, treat that as if it's talking about the previous term. So in words, I would say that this is the current equals our previous times 5. So notice I went from function notation to the word format. And it's also saying if f of 3 equals 6, find f of 4. Well, if f of 3 is our previous term, and we are trying to find f of 4, we know that we can rewrite this a little bit. F of 3, we know that's 6. And 6 times 5 is 30. That one's not too bad. Of course, you'll explain your work and say, maybe I put this in words and I plugged in for n, or f of 3 over here. Hope that helps. You have your now explicit. So this is an explicit function, because no matter what we plug in for n, we're going to get some output. We don't need to know the previous term there. So this is pretty simple, just 5 times that 4 in place of n. It's equal to 20 minus dose, 18, boom, the age to vote. Pause the video, copy this if you need it. Let's keep this party going. Having a good day. I just want to keep going with these. If you want to find the 5,000th term, which of the following types of equations would be the easiest? This is a flashback to what you saw on 1.3. If you check my camera, questions like that, 7 through 12, that's very similar to what you have here. So if you want the 5,000th term, if it was recursive, you would need the 4,999th term. I don't have time for that. I don't care about that. So explicit's actually the best to use here. Reason being, there you go. That's enough abbreviation for you, right? Because I don't care about the 4,999th term. So that's why recursive isn't a good look. Explicit, you can plug in for any term. If you know the 60th term, want to find the 61st term, which of the following makes sense? Well, you have the previous term, the 60, and you're aiming for 61. So simple recursive. Boom. What's up with the rest of this? You got this sequence here. You have 5, 10, 20. That sounds like a good amount to get paid regularly for doing nothing. So I know that from 5 to 10, that's adding 5. And then it jumps to adding 10 to 20, which adds 10. So I know that this isn't arithmetic because we're not adding the same number consistently. So this is definitely geometric. Based off of this, it's as if we are adding the previous term. So it's as if we have the current equals the previous times 2, because 10 is 2 versions of 5, 20 is 2 versions of 10. So if we keep this going, next term would be 20 times 2, which is 40. And the next term there would be 80. If there's a common difference, write the common difference. There isn't. And there is a common ratio, because if we take, let's say, f of 2, put it over f of 1, or you could do the current term over a previous term. F of 2 is 10, f of 1 is 5. So our common ratio in this case is 2. Positive 2 at that. Make sense? Look back at recaps if you need to. The 20th term, if you were aiming for that, let's see, you know that you would have to go back to your 0 term. So the 0 term, if we go back, is going to be half of this 5. So we could say that f of 0 equals 2.5. This is consistently working around that. So we are working in increments of doubling. So in words, we're starting with 2.5. So we want to say that no matter what, we have 2.5. And it's recursive, or sorry, yeah, geometric. So we are doubling. And that comes down to what our exponent is, which is just going to be n. So this would be considered our explicit. So notice that I had to go backwards to find that f of 0 term. That's a common thing in explicit. You don't just want to start with the first term. You got to go back to the beginning. And again, I got this 2.5 because it is, if we go backwards, It's half of 5, so 5/2 to get our 0 term. Does that make sense? You can always email me if you're not too sure about something. Clearing that out. For this problem, see what's up with it. I can see pretty clearly that the rain is gone. It's not the right lyric, but you got it. We keep adding 3, so it's arithmetic. Complete the table. We keep adding 3. 11 plus that 3 gets you 14. 14 plus 3 gets you 17. Common difference is positive 3. And do they need anything else? 30th term in the sequence. So we would need our equation for that. So we would need to find our 0 term. So anytime we're looking for like the term down the way, especially the 30th term, you don't just want to keep adding and adding and adding, make an equation. So if we backtrack our 0 term, gonna write in here, 0 term, deducting 3 is -1. So this is always working with -1, and we're always adding on 3n. So that would be our explicit. And if we're aiming for our 30th term, big 30, it's checking for 30, right? Yeah, 30th term. Okay, cool. We could take -1, which is still there, plus that 3 times that 30, -1 plus 90, getting us 89, feeling fine. So that's f of 30, the 30th term. Does that make sense? I hope it does. Pause the video, write this if you need it. Cool, another one. We're starting at 2, we're going back, and we keep deducting 6. So this is definitely arithmetic. I know we're deducting 6 because we start at 2 and go to -4, -4. Sorry, -4, -10. So if we keep deducting 6, this is going to be -22, feeling blue, -28, feeling great. Common difference, -6. And then this is asking us, oh no, we're good. Okay, yeah, that's it, done. Pause it if you need it. Create a table that would fit the recursive rule. All right, I like that. So they give you a freebie, meaning me. I gave you this freebie of f of 11. So you would want to throw that in here. And let's break down what this recursive rule is saying. So f of n, we always call that our current. And this is equal to, in this case, f of n minus 1, which is our previous, and plus 5. So this means that as we move forward, we're always adding 5. Again, assuming that n is adding 1. And that seems to be the case here with this table. So we'll just go our merry way. Just keep adding on 5. So 11 plus that 5 gets us 16, gets us further to 21, to 26, 31. So much fun. Let's go backwards for the 0 term. Although they put in f of 1 is our starting term, I put air quotes around that. F of 0 could have also worked too, but in that case, it would have to be 6. Boom. So recall that I took apart the set notation or function notation, not set notation. Current, we always use that in place of f of n. Previous, we can refer to that as f of n minus 1. Boom. So notice that we didn't have anything here really with exponents. That was kind of not asked of you to find an equation that had that going on. So I hope that helps. If you have any questions, of course, reach out. I'm confident you can all do this. Everybody can math. Let me know if I can help. Thanks for watching.